fondatore e l'amministratore delegato di Maxeler. Maxeler è una società che ha una sede a Londra e qualche ramificazione internazionale. La ragione per la quale noi siamo entrati in rapporti di lavoro con Maxeler è perché abbiamo svolto un progetto importante assieme nel settore oil and gas. Mi sono dimenticato di mi devo presentare. Io sono Ernesto Bonomi e sono dirigente di ricerca al CRS4 e mi occupo del settore energia e ambiente, no? Ed è nell'ambito di una delle nostre applicazioni di questo settore che abbiamo iniziato circa 2 anni fa una collaborazione assieme a loro, e questa collaborazione è stata finanziata dall'ENI e l'obiettivo era di sviluppare un applicativo che richiedesse ingenti risorse di calcolo e che elaborasse ingenti volumi di dati ovviamente nel più breve tempo possibile. Questa storia, questo nostro legame, diciamo, continua ad avere un seguito. E la ragione per la quale Oskar, Mencer e Diego sono venuti qui è per vedere se ci sono le condizioni e lo spazio per aprire una sede qui in Sardegna, e ovviamente sono alla ricerca anche di personale. Ecco. Dunque lascio la parola a Oskar. Oskar farà un'introduzione, farà un seminario, una parte del seminario per quello che riguarda la storia della società, il core business della società. Non l'ho detto, ma diciamo la parola chiave è FPGA e Oskar ci dirà per quale ragione questo FPGA lui l'ha percepito come una buona opportunità di business. Dopodiché Diego darà un seminario che sarà più una sorta di tutorial per illustrarvi in un'applicazione l'utilizzo di questo tipo di architettura. Here you are.
Thank you, Ernesto. Thank you, everybody, for joining us here. Also, for everybody listening over the internet, the rest of the presentation may stay in English, I think, because my Italian would be finished after about 2 or 3 words. So the title of this talk has been reconfigured a few times since it was first circulated, and we finally agreed that the best way to name it is reconfigurable data flow computing, because at the core of what we're trying to do is really shift the focus in computing from control flow from microprocessors over to a data flow-centric computational model where the data is flowing around the system and the programmer manages the flow of data as it is moving around. And so I'm going to start a little bit by introducing the company and where we do what we do, and give some examples of what we've accomplished in the last few years. And then Diego is going to take over and show a little bit of how things are actually being done, what the programming models are, and how one can interact with the systems that we are building. So from this picture, we see the slightly distributed nature of our activities. We have activities going in Silicon Valley, in New York. Most of the activity today is in London, so I would say the biggest part of Maxeler is in London. And then there are some activities as well distributed in other places close to where potential customers are and where potential activities are going on these days. In terms of what we do, we are a vertically integrated company, which means that we do math, algorithms, hardware, software, optimizations, all the way down to the gate level, the arithmetic level, in 3 basic chunks. We build hardware, we write software, and we have the consulting services, which we build around these two to provide the complete solution to our customers. So rather than selling products, we're providing a complete solution to the problems that our customers are facing, which are not necessarily computing problems, but they are scientific problems. They're problems of solving a partial differential equation, optimizing an activity, figuring out the shortest path through some computational problem, and various business issues relating to these. And so pulling all of these different parameters together, coming up with the optimal computing solution to the particular problem, which may move computing from a data center into the office environment, from the office environment back into the data center, reorganizing how things are being done within the customer company, all falls within the consulting part of the activity. In general, if you look at the acceleration part of things, this just shows one of the processes that we are following when accelerating applications, where we take the software from our customers and we build custom machines to make them go as fast as possible. And what that means is that we need to do the analysis of the problem, the analysis of the software that we are given from the customer. We have transformations that we do on the algorithm level, also on the source code, on the loop structure, on the I/O versus memory versus computational balance, on the communication versus computation balance, all the way down to partitioning the problem into different nodes within the node, into source code that runs on a microprocessor versus on various accelerators. And finally, looking at value generation, where we see where does the value really lie in that computation and how much money needs to be spent in order to accelerate something by a certain factor. In the abstract of this talk, you saw a discussion on the memory wall and the power wall, which are fairly well-known concepts at this point. The microprocessor community has run into issues with different speeds of memories versus the microprocessors. The scaling is very different because these technologies are inherently very different. So if you look at the parallel processing elements on a particular chip, today we're talking about multi-core processors, they all have to share the same pins of the chip. And there's a physical limit how many legs you can put onto a chip that is of a certain size. So regardless of how many more processors and transistors you can fit into the chip, you will always have to go through these legs in order to get onto the printed circuit board. And that causes a fundamental limit of how much parallelism and how much performance you can fit into a particular chip. And if that wasn't bad enough, there is also a power wall, which means that as your transistors are getting smaller, your wires are getting smaller. As your wires are getting smaller, your resistance of these wires is going up, and the heat dissipation to get signals through these wires is going up, so you cannot make wires infinitely small. The smaller you make them, the more trouble they're causing, and the more easily they can burn through. And so that contributes together, of course, with much more transistor switching at higher clock frequencies to the power wall that we've run into. And we've seen over the last few years that this has actually happened. Intel is not selling microprocessors that are running at higher clock frequencies anymore. So you've bought a 3 gigahertz processor a few years ago, you're still buying 3 gigahertz processors today. Now, one of the things that we started in the beginning looking at is what kind of challenges are there that really require computation in order to make a significant difference in this world. And so one of them is oil and gas exploration. If you want to find oil underground, you need to be imaging underground. So you're looking on top of the surface and you say, well, it's very hard to tell where one should drill. If you want to drill in any of these places to look for oil, it may cost between $50, $100, $200 million. So you better get it right. And so what people figured out is that the best way to do this is to simply create an image of the Earth underground. And that is basically done via computation. So this is a nice image for how this is being done on the ocean. There you have a little boat going there on the left. That little boat typically has 1 or 2 helicopter landing pads and carries the world's largest moving objects inside. So the image here really is a little bit misleading. These boats are relatively large. You look at the cables in the back. they stretch up to 10 kilometers. And these are 10 kilometers of sensors that are being pulled. This little boat there has to be able to hold 10 kilometers worth of cables inside its trunk. So they end up being fairly large. What they do is they have a source up on the left. There is an acoustic wave being generated that goes down through the water, hits the ground, goes into the earth, bounces back up, and hits the sensors. So all of this data is being collected up at the sensors. The sensors collect maybe something like 100 terabytes of data. And these 100 terabytes of data need to be processed somehow. And so then you need to move 100 terabytes of data from that boat over to a data center, which is not done through a communication network like Tiscali would be having, but instead has a much faster communication network, which is based on the helicopters taking the disks and actually flying them over to the data center. So it's a very extreme way of communication, but it seems to work for them. In this image, you can see the different bounces of the waves as the acoustic waves hit the different layers of the earth. And that is really what you end up seeing at the sensors up on the top. And then finally, you get images like this one on the right, which is the data basically collected from these geophones. To make things worse, there are multiple ships these days. Let's say 4 ships, each carrying maybe 10 or 12 of these cables behind them, and each one of them being 10 kilometers large. There is a lot of data being collected. And so the computations in order to get that image that you see underground here can sometimes take days, weeks, or even months, depending on how fine or how coarsely you're modeling the physics underneath. I'm not going to bore you much more with this. A lot of people here already have seen this many, many times over. The interesting thing from our side is this is from a paper that we've published together with Schlumberger at the Hot Chips conference last year. And you can see the requirements of the various algorithms that are being used to image the Earth. And you see that the relative computational cost going from a simple acoustic wave to VTI and TTI, which are starting to model various elastic properties of the Earth, increase the computational requirement by quite a bit. And this is for a 30 hertz image. What the 30 hertz means is that we are imaging at 30 hertz spatially, meaning the grid of your image has a certain frequency in space. If we want a much nicer image like the one on the right, so you have here that one image which is at 30 hertz. If you want to have a much nicer image, you can go up to, let's say, 60 hertz. Suddenly your computational requirements go up significantly. And this is only going isotropic VTI, TTI. The next ball up there to the right would be elastic. You can go viscoelastic. And so there's a lot of computational requirement that is out there that would require very high amounts of computation. You can see that here it takes thousands of nodes and 5 to 7 days. While if you want to go to the right, it would take 15 to 20,000 nodes and also several days to compute this. So the computational requirements are immense. And so here are the solutions that we are providing in order to resolve these issues. What we are changing here is the focus in the programming model. If you have a microprocessor, you have instructions, and the microprocessor reads instructions and reads and writes data and does the computation internally. Instead, what we are doing is we are creating a data flow graph. All the mathematical functions, you have additions, multiplies, you could have all kinds of functions that you're computing in there, like sine, cosine, and have the data flow through that system in one big loop, so that you're accessing the memory in a nice strided fashion, nice regular fashion. You get the most performance out of your memory system. And at the same time, the data flows through these networks of functions. The computation actually happens as a side effect. It doesn't actually take any time to do any of these computations, because the amount of time it takes for the data to flow through this is the same with and without the computation. Right? So if you access, let's say, a terabyte of data, the fact that it takes 1 second or half a second or no time at all to go through the chip is completely irrelevant, because the time it takes will be determined by the time you need to read the 1 terabyte of data from your memory. So having such a computational model allows us to run things fast, and we're going to see some examples of what fast really means and how fast we can do these things. In terms of architecture, you have to imagine a CPU with memory going through a PCI Express bus with acceleration cards attached to that PCI Express bus, which is a fairly standard architecture that you can see with a lot of different technologies. You have computational kernels, which have the data flow implementations in them on each one of the cards. Each one of the cards has some memory, and there is also an interconnect between all of these data flow graphs across the card, which we call Maxring. In more concrete terms, what we end up putting together is complete racks, which we call max racks. They come in sizes of 10, 20, and 40U with noise cancellation, without, various features that people have requested so far. We built the boxes ourselves, and we built the cards ourselves. And so there is 3 levels of optimization already in the system. Inside of the chips, we are then building the arithmetic ourselves and the architecture of these data flow units ourselves. So you get to accelerate vertically across the entire application, all the way from the arithmetic unit, all the way up to the way that the network works across your whole rack. This is just providing some more details on the actual hardware, which is interesting on the memory side. If you look at one of these cards, it has 96 gigabytes of data space. Put 4 of these cards into a box, you have a 1U box with, actually this is the 1U box for the previous year with the 96 gigabytes, so you have 1 card with 24 gigabytes, sorry here. And if you put the latest and greatest memories up there that are coming out this year, this number goes up to 200 gigabytes. On top of that, you have a node which also has 100 gigabytes of host RAM, and so you end up with 300 gigabytes right there. On top of the 300 gigabytes, you can now think of memory controllers which are sitting inside of these chips that we are programming, where we can have custom memory controllers that are optimizing the way that the data is being represented and accessed. You get compression ratios of 2, 3, 4, 5 times, meaning that you can actually hold over 1 terabyte of data inside of one of these boxes. So once you have access to 1 terabyte of data inside of a 1U box, what you end up having is a memory machine that holds your entire problem inside that 1U box, and all you have to do is access it, rotate it through a computational engine, and you don't need to worry about communication between nodes, how fast your network is, and optimizing your parallel programming capabilities. So what have we done with this? Here are a few examples in oil and gas, also in the finance industry. Let's start with the easiest one. So the easiest one is convolution, which occurs in most applications. In fact, I'm starting to believe that any problem in this world can actually be solved by convolution, and somebody has tried to solve it with convolution. This is a 3-dimensional version of this activity, where you have a stencil on the upper left. You're moving the stencil across your 3D domain. You can imagine that the problem that you have is the size of your cube. The larger your cube, the harder it is to compute. The larger your cube is, the less it will fit into your L1 or L2 cache. It will not fit into the main memory of your node. You have to partition across multiple nodes. If you imagine you have a 3,000 by 3,000 by 3,000 cube, and you may have 5 to 10 such arrays, you end up having 10 or 20 gigabytes right there in your data space. So instead of putting all of that into your node, if you put it onto one of our cards, these are the speed-up results that Chevron obtained in 2008. You can see that one of these cards corresponds to between 100 and 250 of the Intel CPU cores that you can buy today. Now, the difference here is, on the left, the domain size is small. You have a 200 cubed problem. As the problem gets larger, the CPUs are getting more and more inefficient because you're missing in the cache, missing first in the L1 cache, then you're starting to miss in the L2 cache, then you're starting to miss in your main memory, having to go between multiple nodes. While with the machines that we're building, you get up to a terabyte inside of a node. You don't have to go through the communication network. All of the memory is accessed in one singular raw fashion through the DRAMs. So that's why you see the performance going up as the problem gets larger. And this is what actually happens. So you have a wave, it propagates through, this is this explosion at the back of the boat, and it goes through, there is a salt body here, and you see that the acoustic wave moves at a different speed inside of the salt. And what all the oil companies hope is that under the salt somewhere, I was told, is the oil. And you have to find it somewhere there. And so the different imaging techniques are really helping you to get under there. Nice features of this solution is that it runs at 150 megahertz, and it gives you a 30x faster solution than if you use regular microprocessors. What does that mean? It means that a 1U node that is this high with our cards in it for this particular problem, running at 150 megahertz, does the same computation as a whole rack of Intel CPUs standing this tall, filled up with the Intel CPUs. If you have a data center that has a state-of-the-art air conditioning where you can actually fill up your rack with Intel CPUs, which most people wouldn't even do. So as a consequence of the 150 megahertz, rather than computing at 3 gigahertz, if you look at the equation for power consumption and for heat dissipation, you see that the clock frequency is a key term in there. By computing 20 times less clock frequency, you have very low power consumption, and you basically reduce your operational costs almost down to zero. So if you have an electricity bill of $2–3 million a year, you're going to be down to a few $100,000 with using this technology for the same computation. Here's the next step after that. We moved up in scale and implemented a 70 hertz imaging algorithm. Now you've seen from the previous slides what that really means. It means the images are a lot clearer, nicer. This is a project that we've done with Annie and with Ernesto's team here at CRS4. And you can see in the blue case, which is the 70 hertz imaging case, we get 8 of the Max2 cards to replace 2,000 CPU cores from Intel. So that shows that as the imaging quality goes up, the benefit from this type of technology increases very dramatically. If we turn that into power consumption, you can say that 8 full Intel racks burning approximately 100 kilowatts of electricity now get replaced by 2 max nodes, which is a 2U system about this high, burning less than 1 kilowatt. Another application here that is quite curious, I've watched Annie present this algorithm at an oil and gas conference a few years ago. And the story was that it would basically take a few hundred years to compute this algorithm if one was to follow this math. And Annie got together with CRS4 to develop an algorithm that would, or a solution, an implementation of this algorithm that would run in a much more reasonable amount of time. But it was still not fast enough. And so last year, I believe, we put this, this application into production, which runs on I believe, 100 cards from Maxeler, and gives a speed up of 230 times in case of land acquisition, when you have trucks and you're trying to image the Earth on Earth, image the Earth on land, versus the marine case where we got the 190x speed up for the same application. And you can see the different images, which are very similar to each other. So one would say, okay, so this is convolution. We've seen convolution can be done in data flow style. It's relatively trivial. Everybody knows you can do convolution. What nobody can do is sparse matrix computations, because sparse matrix computations have the issue that you have to solve a linear system sometimes, and it doesn't scale. You see here, these are results from Schlumberger again, which they presented at the Hot Chips conference with us last year, as I mentioned. And it doesn't scale up. You see it goes up for a while. After 6 cores, the performance is the same. So buying more computers is not going to help. It's just not going to run any faster. This is for a geomechanics application. They have Eclipse and Visage results here, which are 2 products from Schlumberger. And you can see the same thing for a finite element method benchmark, where the scaling just isn't there. So buying more computers doesn't help. We've done a project here as well. If you look on the left, you have a sparse matrix that looks like this. And as part of the iteration, every time step, you have to solve this linear system of this sparse matrix. And on the right here, you see the speed up that we've obtained. There is a patent pending on how we've actually encoded the matrix and the data inside of this problem in order to be able to get the speed up of 20 to 40x per 1U at 200 megahertz. So what this means is 1U, one of our boxes, is 20 times faster than the 1U box that you would get from Intel. If you look at this, there is no way to get 20 times faster with the Intel solutions because the microprocessor solution doesn't scale up at all. So now it's not just equivalent to a larger number of Intel processors, it really gives you a turnaround time that is not feasible with microprocessor technology. Here's another example of changing what can be done. This was done with JP Morgan, where we are computing credit derivatives, and the key question is, as the world moves on and countries are threatening to default, and you say, well, is Greece going to run out of money, or is Portugal going to run out of money? What is the impact on one of the large investment banks and their credit portfolios? And so they need to be able to compute the risk and the value of their portfolios in real time. What they could do before is to compute it overnight. So there's a data center, and in that data center, you take 8 or 10 hours overnight to compute it. And if you're lucky in the morning and nothing happened, there was no power break or none of the computers broke, you get the result, and the trader comes in the morning and uses the risk numbers for his trading during the day. If something happened during the night and there are no numbers, then he has to wait for the next day. He's going to be trading blind for a whole day. What we did here is take that computation from 8 to 10 hours and move it down to, where is it here, maybe in a few minutes. So there's some detail there with 3,000 bespoke branches, which mean a lot to the finance community and may not be as easy to explain here in a minute or two. But the simple story here is that we got 220 to 270x speed up, around 30x in terms of space and power consumption, meaning that the solution that was computed overnight can now be done in a few minutes on a workstation, on a trader's desk, during the day. When the CNN news hit, he puts in a few new parameters, he pushes a button, 5 minutes later, he knows what his risk profile is, he knows what he needs to buy or to sell. And so that really doesn't just accelerate the computation, it changes the way that the company can operate. It changes the thing they do, it changes the way they're doing their things. And that's really the exciting part about making computation go a lot faster. We had a summer intern looking also at the Smith-Waterman algorithm. I'm not going to spend too much time on this, but this is just a very generic Smith-Waterman example. And we have here some comparisons to various technologies. You can see here, again, one Max3 node with 4 cards gets us to 240,000 cell updates per second, which is maybe 200 times more or 150 times more than the raw CPU numbers for an Intel node. So the next part of the presentation is about how we actually do this, and Diego is going to take care of the programming side of things. So I'll say thank you for now. Oh, Ernesto is suggesting maybe questions in the middle of this. So if you have questions now, you can also ask later. Any time is good. Any? Okay. Yes. Okay. 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 Mm-hmm. Oh.
Thank you. We already do a project similar to that in Monte Carlo real-time computation for medical physics application. I have a question about your compilator, because I understand that you start from a Java script, it's correct? Java language. And so, okay, I'll wait for you, because I know how it's difficult, for example, to do a square root or logarithm on a trigonometric function. Okay.
Yes, so the programming model is coming as the next part of the talk. So if you have questions after that, it would be good to hear. And yes, another one.
I think this is probably, it's Paolo Meloni. I'm a researcher at University of Cagliari. Just when I heard about reconfigurable data flow and application-specific data path, saving power and a lot of other keywords that you use, it comes to me also in mind that maybe some of your technology can be used also for different application domains. So did you ever try, for example, this technology for embedded systems, for portable systems, or your key area is only high-performance computing, and you, okay.
So definitely there is a large scope to employ this technology for the embedded space. However, the different spaces are really very, what's the right word? They're religious domains in which people have a certain way to think and a certain way to solve problems. Our system is geared towards scientists. So when we program these systems, we have geophysicists, physicists, mathematicians programming these systems. Our programming environment is targeted to be useful and applicable to that domain. Embedded systems people would not like what we do because it makes what they have studied for many years not applicable. So if you have to learn for 10 or 20 years to do something very difficult and somebody makes it very easy, that is not going to help you. Because all the stuff that you've learned now is not useful anymore. So embedded systems community has not been very excited about this progress. We are trying to work with people who have not worked with this technology before and have not invested any energy, making their life easier to give access to this. The other thing is that we built hardware systems which are supercomputers. You cannot take a supercomputer and make an embedded system out of it. We are working on kilowatts and megawatts rather than on milliwatts. And so the technology that you're building and the way that you're solving problems is very different when you talk about kilowatts and megawatts as opposed to milliwatts. And so the science behind that is a little bit different as well. So these are kind of the answer. Any other questions? Right, Diego.
I think I'll stick English if you don't mind. Yes, if you're all right, guys. So a little bit of my background, Diego Riato. I started to study electronics engineering here in Italy. Then I moved to London, where I did a PhD in physics. I then joined IBM. I worked at IBM for 7 years to develop the IBM middleware. And then I decided to join Maxeler. And funny enough, in Maxeler, I'm doing the three things at the same time. We're doing electronics because we design our own cards. We do developing because we developed the Max compiler. That's the tool I will present in few minutes. And we use actually Java. That's exactly what I used in IBM. And I'm doing a lot of physics because we do have to work with people like Ernesto, that they are gurus in the field of geophysics, for example. So I need to know what I'm talking about when I'm going to a meeting with Ernesto. So it is a very challenging job. And you have to put all the three things together and come out to do something that no one else could. So acceleration. Is this a problem? Yes, it is. It is very hard to solve. And the way we think about it is we cannot tackle one single problem in acceleration. We need to go through all the stack. We need to design our hardware, design our software, and understand our application. And unfortunately, we believe it's the only way. The good thing is Maxeler provides a lot of tools to do this. So Oskar discussed about data flow computing. And that is basically the core. When you understand this one, you know what exactly we're doing. So what we create is a graph. We know what kind of instruction. If you think a CPU, what it does is a read an instruction, decode it, execute what the instruction is about, like an addition, take the data, put together the data, and then it is finished, just to do one instruction. Our approach is we know which instructions are costly. We know exactly what we need to do it. We just lay down all these instructions, one after the other, and we connect the result of one instruction to another. We create a data flow. Now, if we're able to do that, the only problem is send the data in. It's like a coffee machine. Put the water, you got your filter, then comes your coffee. Easy as that. It's creating this one that makes the difference. And why do we want to do a data flow? Thanks. And how do we get the acceleration that you saw in the previous example that Oskar presented? Well, simple. We do what the CPU does usually for us. We just put a little bit more cleverness in our application. So if you think of the CPU on the left, is a very complex system. Each core, now multi-core CPUs, has to have its own infrastructure. And at the top left is the execution unit. It's the only part of the silicon that is actually doing the work you're interested in, like adding two numbers. With our data engine chip, it is all laid out there for us to add logic units like adders, multipliers. We actually have basic elements like memories available, like a cache inside the CPU, and we have multipliers and others. They are available to us. What we need only to connect that. So that data flow engine allows us to create the graph physically, what we actually built previously from all the instruction, we create the data flow graph. And this shows the difference in size. So a CPU will have only that small part available to actually put some logic and do instruction. Maybe superscalar, pipeline, but still a very little silicon area. We have all that. Well, we take a little bit to put our logic to interact with our data flow engine. But the main part is there available for us to use it, to put real useful instruction. So we will show an example to explain again this concept of flow of the data flow engine. We take a simple 3 points average. So we have a very big train of data coming in. Every time we take three numbers and we do the average, and then we send out the result. A piece of code illustrates what exactly we do. And this is what we create. So we have tools that create this graph that are now represented with some boxes, white ones where there's a plus and division. There are some diamond shapes that represent looking back and looking forward in your stream of data, getting the previous or the next value. And the top is the data coming in. So as every tick of a clock in our engine, the data moves through our graph, and the result comes out. Simple as that. If you have the graph, we have the solution comes out. So what you do, this is how our data flow engine interacts with your application at runtime. So your application will be run still in the CPU. CPU controls exactly your software. The things that we do accelerate is usually a very small part of the application, the part that actually is very computational intensive. So in order to do that, we move that part into our data flow engine. We create that graph structure, you saw it. And then we move the data into the memory of our data flow engine card or system. And we stream the data as you saw it. The interaction goes through PCI Express, communication to CPU and to the memory of the system. So our engine, it looks like a coprocessor that is communicated via PCI Express. And this is maybe start answering the question about this Max compiler, how we create these graphs. And this is how we do it. So for example, for the 3-point average, we decide that is actually the 2 addition and division that is the part we need to accelerate. So we represent it in Java, and we create what we call a kernel, so a unit of logic, where in this case the 2 adders and the division. Then we create another Java file, a Java class, that represent a manager. A manager usually connects kernels to the outside world or to the onboard memory of our accelerator. So basically, we need to create 2 objects using Java, object-oriented programming. Then we run our compiler. The compiler generates a binary file that is used to program at runtime our data flow engine. And that's what you use. You take the result of your compilation, you link it to the library as a library to your executable, to your application. Then the application will be enabled in that way to run your 3-point average in your data flow engine, or you could actually choose not to do that, or you could do both at the same time. Not sure that is clear from this picture, but we can come back later if you want to. So what do we use to create our graphs, to implement these kernels that represent the logic of the program that you want to accelerate? We use a simple Eclipse-based tool. We extend Eclipse with plugins. We have our own implementation in Java that is an extension with the operators overload, nothing fancy, it's just Java. Make it easier. And that's what usually we're programming. This has the ability of simulating what you're actually producing. So your kernels can be run simulation in Java, or you could choose to simulate this one in other ways. How do we do? So let's have a look at the development process. So this is your code. That's the code that you have. It's 3-point average. And at the moment it's running as a C file into a CPU. So as I say, we create the data graph. we describe the same code is on the right. This is HWVAR, all those things, just Java object. We actually can use it. As you see, we implement in a very similar way as the original code. And we define an input and an output, input X, output X, Y. We have some stream offset that is the previous and next definition in the stream. And we add them together and we divide by 3. So basically, it is the only things you need to do in order to accelerate your application at this point. You describe your kernel, the computation in your kernel. Then, of course, you need to create the other file that is the manager. The manager will only define some links. So you say X is attached to PCI Express. Y is PCI Express. So your data will come from CPU through PCI Express in your data flow engine, then the result will come out and be available to your program. And then what do you do to your regional application? Well, you remove the code that you want to accelerate, and just with a simple library calls to our runtime environment, you call our device, you send some data. So in this case, X and Y are arrays. And that's how the flow works. So you send some data from your main memory into our device. The data is processed and then comes back in this way. What about if you don't want to use PCI Express because you want to keep your data into the memory of the engine or the data flow engine? Well, for example, you want to keep the result inside your data flow engine card. Well, you tell, using the manager, you don't want a result out of PCI Express, but you want to keep it inside. So in this case, you connect the result to the onboard memory. You could reuse it for next computation. So that's basically the piece of code that you've seen. Each line of this Java code creates one of those elements of the graph I've been describing so far. So Java becomes a descriptive language of a graph. And your purpose is to connect each operators to the next one so the data flows in a nice way. This concludes the overview of the Max compiler. Is there any questions on this one? I know there are many. If we come back to your questions.
I have a main question because please go back to the previous.
Yeah, that's fine.
My experience to do a division in floating point, I need at least.
That's correct.
So I cannot see here how you do that.
Well,
another question is, what is the interface?
okay. So in the old way of programming the FPGA is using VHDL. So the great about our tool is I've been working for 3 years and I never done anything in VHDL. So we done all the work up front, all the operation, division in this case, is implementing the VHDL is reusable through just the Java call, as you see on the left. So we have a specific division, floating point, fixed point, all these have been implementing already. So you will just have to use it as a library, nothing else. How efficiently I've done, well, we have experience in this one. We've done a pretty good job, we believe. Oskar, do you want to add?
So maybe I can add to this particular story. So this is really all the code you're ever going to write. When you compile this, there is 1 million lines of code in our compiler that takes care of taking this and making an FPGA circuit out of it. That includes a large number of optimization algorithms, ILP formulations, arithmetic optimizations that we are doing, a vast amount of libraries and components that are all being compiled together, all in order to make this programming environment accessible to geophysicists. At Maxeler, people who program FPGAs have never seen VHDL and have no clue what an FPGA is. This is the 4th generation of a programming tool. The 1st generation or the 2nd generation already outperformed absolute VHDL experts by about 2x. And this is an experiment that I ran over at Bell Labs with a team that was developing products for Lucent. And we had their IEEE fellow, the best VHDL programmer they had in-house, develop a circuit, and we took a C programmer who had no clue about FPGAs, implementing a multimedia algorithm for imaging. At the end of the day, the compiler spit out something that was half the size than the best thing that the VHDL programmer could ever generate on an FPGA. So the myth that you can write the best assembly code by writing the assembly instructions yourself, or as Howard Aiken would have said, maybe if you write the zeros and ones yourself, that you can do the best job, is not true as the complexity of the circuit increases. As you create a circuit with maybe 5,000 arithmetic units, you cannot optimize the entire thing by hand by writing one little bit at a time, but rather can write tools that optimize the whole thing by using strong optimization algorithms like ILP formulations, maybe some simulated annealing, spitting out, taking this source code and maybe spitting out a few thousand lines of VHDL which have passed through the entire compiler, which then go into the Xilinx tools. So,
and the second question that you had was the interface between the Max compiler and the Xilinx tools or whatever vendor FPGA is that it is VHDL. So the VHDL is what is generated automatically by the Max compiler, and then the FPGA vendor will take that and create a bit stream for it. Do you want to elaborate? Is it? Okay. Any other questions on the subject or anything? I don't know, Oskar, if you want to say a few words regarding this slide. So that is the almost final slides.
So this just shows the scaling of the technology if you look into the future. Of course, if you've seen the image of the FPGA before, making a larger, better, faster FPGA is a copy-paste activity. You simply take a few lines and you copy them. Because it's a chessboard, you can always scale it up to be any size you want, and it becomes a manufacturing question of what you can manufacture and what you cannot. So based on projections, you can see here the next 10 years, or at this point only 7 years, of progress of the technology, which shows that speed or relative performance is still increasing dramatically, and we are not about to hit any major performance bottlenecks at this point with this technology. So we are expecting about a 2x every 18 months or so for the foreseeable future. So that's the core technology progress. There was one question on what else could be done. There is a wide range of activities that would be very exciting to do. Since we're here at Tiscali, maybe most interesting to talk about application-aware communication. If you think of a communication network around the world and you have nodes that are forwarding data from one place to another, if you can make the network aware of the applications that are going through, you can create a lot more intelligent applications. And so, for example, this would consist of having an intelligent router which could assemble and disassemble a packet as the packets are moving through. If you have a programmable interface to then do something to these packets, you can route communication packets, let's say telephone conversations with Skype, from one side to the other by knowing that this is a telephone conversation and moving it around in a certain way. Medical imaging is very similar to seismic imaging, except that you don't have one surface, but you have the entire surface around the body, and of course the dimensions are a little bit smaller. Weather forecast, various earth science applications that are quite critical. We've nowhere scratched the surface of the computational requirements for weather forecasting. There is, of course, genetic algorithms, bioinformatics, which has significant problems still to be solved. And there's also a variety of others like animated movies, television broadcast, all places that require a large amount of computation and have very large amounts of codes, things like hundreds of thousands of lines of code that need to be programmed and run very quickly. So that's the summary here. We've shown some examples of computing 30 times faster in terms of computations per cubic meter. Computing at much lower power consumptions. We've shown that a lot of different types of applications can be implemented with this technology, and that it is possible to program these types of systems without spending 10 years and 500 people on it. So that's the summary, and we have any more questions on either the programming side or the applications? Antonio, you would be heard across the internet by millions of viewers outside. Let me pass the microphone.
Intanto se devo parlare parlo in italiano perché in inglese non è proprio il caso. No, l'esperienza nostra con la Maxeler è stata decisamente positiva. Perché diciamo che non si è trattato soltanto di un porting di un codice portato su FPGA, ma di metter mano proprio al codice per vedere là dove si poteva intervenire in modo tale da massimizzare il conto all'interno dell'FPGA. Per questo c'è stata un'ottima interazione. E poi il risultato si è visto, insomma, si è visto perché il codice che poi è stato realizzato è attualmente in produzione all'ENI, sta producendo i suoi risultati, quelli che deve produrre, sicuramente in modo molto più veloce di come poteva far prima, anzi prima probabilmente questi risultati non avrebbe proprio potuto produrli perché non ci sarebbe stata la possibilità. Non so.
We used bridges, already commercial bridges. What is that? I don't remember.
Can you say something about the application?
Yes, our application. Perhaps can I give you some paper of our project? I want to cooperate with you. How much does it cost? Yeah. I'm very interested because perhaps we did the same way did you. but in a very small scale. The question is, how did it work, the bridge between the PCI bus and the FPGA?
I'm better at this, all right. Diego doesn't actually know about the hardware, anything. He's programming the systems from Java. We have a team of 10 hardware engineers. Yes. So we have a team of 10 hardware engineers which are building the cards, and they're building all of the communication interfaces. We write our own DDR3 memory controllers for each array of the applications sometimes. But in general, there are generic components for that. Our PCI Express controller is something that we've developed in-house, of course, in VHDL and on the low level. Programming our systems, you don't need to know about this. So this is part of the complete system solution. So all you do is you say, data go over PCI Express, and our infrastructure will take care of everything. So that's why there is a compiler team of 10 people writing the compiler and maintaining the activity, and there is another 10 people maintaining the hardware and all of the interfaces so that we can run DDR3 at maximal speed, PCI Express at maximal speed, utilizing all of the slots on the bus, keeping the utilization high. On the operating system side in Linux, scheduling the threads so that you're accessing the data in a continuous fashion so that the CPU can compute at the same time that you have a PCI Express transaction, at the same time that the FPGA is computing. All of this has to be scheduled, managed, and in real time shared. And so that is being done by Maxeler OS, which is also written by the hardware team. So there's a lot of infrastructure which is for supercomputing, very specific for the types of problems that we are dealing with many terabytes of data, which is specific to floating point, being able to deal with the floating point operations that you deal with natively, rather than having to build floating point out of lookup tables or adders or multipliers. So it's really the support infrastructure which makes it seamless to use this. Your question with the universities, there is a good answer to that. We have a university program that just started a few weeks ago, and we are actively looking for universities who would want to join and use our technology. There are different ways to participate. There's a wide range of hardware platforms. There's a wide range of opportunities to collaborate for different applications. And so you can send me maybe an email and I can put you together with the people organizing the university program. And I'm sure that we will find a way to make this work for you. Yes?
Okay, so after this last part of the presentation, again, I mean, I don't want you to push to embedded system domain, but I see a lot of our applications, a lot of the research that you are doing that will benefit a lot from, not from the hardware part of your technology, but at least from this part of synthesizing on FPGA, starting from a very high level specification. So it's more or less the same thing that we are doing, but we have multiprocessors inside the FPGA. So it could be some additional feature to what we have. So for this university program, is it possible, for example, to obtain a trial license about your compiler and try to have some HDL? And so if it is related to this, and if I can ask about that, so what are your perspectives with respect to Sardinia? And so if you can say more about that small link that you had there.
Okay, yeah, so again, if you send me an email, I'll be very happy to connect you with our university program. There is a wide range of options to get trial licenses for the compiler, to get various sizes of hardware. We have Max workstations, which are relatively small and inexpensive, which you can put on the desk. We have systems that go in data centers, which are more complicated. And we have people who are doing a wide range of projects with these hardware platforms, which go beyond, of course, what I've shown here. The Sardinia part is very interesting. The key reason for being here is that we've been working with CRS4 now for several years, and with Ernesto in particular. And we would like to strengthen our activity here by opening up a location maybe over at the technology park just next to Pula, and start up by hiring a few people and having a strong presence here, because we've seen that they're really great people doing amazing work, and we would like to be part of this environment here. And so we've already started a few years ago by hiring people who speak Italian, like Diego. We now have several. But also the idea would be to have a stronger presence here and to strengthen the collaboration, have people from here, give them the opportunity to come over to work at London or in Silicon Valley, at the same time open up job possibilities here, and maybe hire a group of people to do these things. So these are the discussions that are currently going on with Ernesto, and I think he's your best contact locally to figure out what is going on with Maxeler Sardinia. Okay. Any other questions? Okay, well then, thank you. Thank you very much.